in the previous part of the lecture, we actually talked about the missing scenario from the incorrect exception condition, which can result in an invalid account objects with its balance being negative. And we said that one way to fix it, as we demonstrated previously, is to make the error condition more accommodating, which means it can catch the missing case. So now in this part, we're going to show you another way to do it, which is actually better in terms of the design. So always when you're programming with objects, you should always think about what will be the legal states for each kind of objects. So now for us, the only kind of objects we have to worry about is the account objects. So account is actually a class. So we have to think about what should always remain unchanged. So this is where the name comes from. Invariant simply means what kind of characteristic that should remain unchanged for each class, or all the objects for that particular class. So that's something we'd like to illustrate first. We'll explain what class invariant really means conceptually, and then we'll see how we can encode it in Java. So the way to improve from version number 2 is by adding a class invariant to say for every account object, its balance should be strictly positive. And this actually comes from requirements number 1. Let me just remind you quickly. Okay, so now we don't want to fixing the precondition is one way to go, but we'll try another way. So now we want to consider this particular condition to say this the balance. So this will be any context objects of type accounts. We want to make every account object the balance should be strictly larger than 0. We think this particular condition here should be invariance, which means it should always evaluate to true. It should be a theorem basically from your 1090 cents throughout the lifetime of all instances of the account. I will draw some diagram to show you, but let me just give you the definition first for class invariance. So what's really class invariance? Since the context is clear, so we just say invariance when we actually meant class invariance. Towards the end of the course, we'll also introduce another kind of invariance for loops, in which case we have to disambiguate by saying either class invariance or loop invariance. But for now, when we say invariance, class invariant, that's what we meant. So class invariance of a class specify the precise conditions, true or false, which all instances or objects of that class must satisfy. Okay, let me draw to actually show you how you can think of it. And of course, whatever we show as the principle for class invariant for account can be generalized to all kinds of classes and their objects. Okay, let's take a look to see how we can sketch the ideas for class invariant, which is very critical concept. I would say even though we introduce precondition first and then class invariant and then later on postcondition, but whenever you want to review the concept for design by contracts, class invariance is the most critical concept to get through. That's also new to you because you haven't really encountered class invariance in your Java course before. Okay, so now we talk about class invariance. Okay, it's a Boolean condition that will evaluate to either true or false, but conceptually that's how you can think of. Let's say we're going to draw a state diagram of if you actually are in the CS major, you would have taken the theory, introduction to theory of computation, and you learn about finite state machine. If you're an engineering student, that's okay. I'll try to draw in a way that will make sense to you. But I'm going to draw some states with some transitions. So now the way to visualize it, you can think about each state. Each state will just be the values of relevant attributes. In our case, the only relevant attributes for each account object would be balance. But when your class gets more complicated, you will get more attributes for each object. And also we get transitions. Transitions are simply the means by which you can go from one state to another by changing the attribute value, by changing the states. So transitions would be, you can think about it's like a method call, especially mutator. Those methods that actually whose return type is actually void, which means they are meant to really modify something about the context objects. Mutator methods call which intend to modify the state of the objects. Okay, so now we got these two concepts over here for you to actually understand first, and then we'll visualize it. Let's say for the case of our account objects, so the starting state will be how you initialize your account objects. So it could be that, for example, in Java, you might simply say, I simply declare account. Let me not worry about the version number, just in general account. And then I can say ACC, the context object name, is assigned to, for example, new. And then constructor over here. And then I'm going to initialize the balance to be, let's say, 100 over here. Okay, so now you can think every arrow is going to be a transition, and every circle is going to be a state. So state will be circle, and transition will be arrows. Okay, so now after the initialization, the state should be the balance, I'll say B, is simply equal to 100, right? That's the states. You can think about for each state, it's going to contain the values for each attributes. Okay, I'll get to the invariant in just one moment. Okay, and then so now let's say throughout the lifetime. So when I say lifetime, I mean as long as your system is running or before your object's garbage collected. So you can think about that's what I meant by lifetime. Throughout the lifetime for your account objects, you may call accessor methods to actually query about its states. For example, you can say, for example, ACC dot get balance. I'll just say balance over here. Get balance. So this should return back to you 100 without changing the value for the current balance, right? It simply returns something. Okay, so it's like a self loop over here. But now let's see how we can modify the states. So for example, I might say B dot withdraw over here. Let's say $20 over here is legal. Let me only consider legal cases. Cases where you might have some precondition violation, let's worry about it later. So this will result in a different states, in which case I'm gonna have over here B, the balance will now be 80, right? Decrease from 100 to 80, and etc. Right? So you can think about, you can withdraw, and also you can deposit. You can also imagine we also got deposit methods in our developments. Okay, so now you can think about throughout the lifetime, you can call withdraw or you can call deposit for as many times as you like, as long as the object state is considered as valid. Okay, I'll talk about what valid really means. So it can be another state. For example, it will become maybe B is equal to 100. Let's say after we deposit $20 into it, and then you can so on, right? You can go as many as you like that. So that's kind of the that's so-called the lifetime of account objects, and this visualization also works if you think about any object that you might create from your own classes. Okay, so the lifetime. So now, when we talk about class invariants, okay, I'll just say invariant over here, it's going to be some Boolean expression that you can evaluate on every object states. For example, whatever invariant I'm going to define over here as a pink, I can evaluate the expression here on every states of the objects. And for each evaluation, it's going to return back to me either true or false. And invariant simply means the expression must be true every time. If there's any particular state of the objects that's going to evaluate to false for the class invariance, that means you have class invariant violation. Okay. So now, what should be the class invariance? Conceptually, this is a question you got to ask yourself. Class invariant over here, conceptually for this particular case, what does it mean? When an account object is valid. In this particular example here, we know from requirement number 1, you can also go back to your slide to check for requirement number 1, which says the account should always be positive for its balance. But in your particular more complicated example, you should always check either maybe your assignment instruction, maybe check your requirements documents, or check with your customer. What do they really mean for that particular business object to be valid? That's something you have to communicate. Okay, so now for our case, it would be whatever account object it is, let's say ACC, and its balance should be strictly larger than 0. So this is our class invariance. That has to be true for every state. So now what's going to happen is if you try to evaluate that, so now when we evaluate for this particular state, it's going to be fine. 100 is larger than 0. 80 is also larger than 0. 100 is also larger than 0 again, right? So now you can see the invariant is simply true for every possible states for your objects. But so you can think about throughout the lifetime, it could be simply indefinite sequence of transitions over here, assuming that you got enough computing resources. So it can be conceptually, you can think about just got infinite number of transitions, and every resulting state from the constructor, resulting states from the first method call, resulting state from the second method call, and so on. Every resulting state must satisfy the class invariant over here. As soon as the class invariance is not satisfied, you got a class invariant violation, in which case the lifetime of the object is terminated, which means the system has to stop to actually blame somebody. In this case, we should blame the supplier because they haven't maintained the object state to be valid. Okay, that's a very quick conceptual sketch for you to understand about class invariance. Again, whenever you review about the ideas for design by contract, class invariance is really one of the most important thing for you to think about. And later on, when you actually got your freedom to design your own classes, always think about what the invariant should be for the classes. Think about different objects for that particular class at the runtime. What does it really mean for those objects to be valid? Okay, let's see some example for class invariance, and then we'll see how we can encode this in Java. Okay, so now let's say we have a class called CS major students, or it could be engineering major students, right? Could be either way. So now what should be the class invariant for CS major students? So think about for every runtime object for CS major student, for example, Jackie, Jim, Jeremy, what would be the necessary invariants for them to stay in the program? Well, for example, it could be the GPA, assuming that GPA is an attribute of every CS major students. They should be larger than or equal to 4.5. Okay, so hopefully you get an idea. What should be the class invariance for the binary search class? Well, remember you learned about binary search tree in your data structure course. So now what should be the class invariance? Okay, I'll pause the video and think about it. Okay, assuming that you have thought about what a class invariant should be, basically, as to be a binary tree, every node should have at most 2 children. Okay, that's the binary part. In order to be a search tree, it must satisfy the search property, which means recursively, every node in the left subtree must be less than the key of the root. And also every node in the right subtree should be larger than the key for the root, right? That's something you learn in your data structure course. But alternatively, we can think about if you do an in-order traversal of your binary search tree, what should be the resulting in-order traversal, which is a sequence? It should be sorted. Okay. If you're not too sure about this, maybe review your 2011 data structure course, or you can ask me. Okay. Right, so these are just 2 examples for class invariants. We'll see more example as we go on. But always think about for your particular class under your design, what should be the invariant property that should always hold to be true throughout the lifetime for the objects. So now, how can we encode this in Java? Exceptions would not be the way to go, because exceptions are usually checked in the beginning of the execution of the method implementation. So meaning that if the input conditions, if the inputs are not valid, we use exceptions in order to throw errors. However, when you say class invariants, it's basically to say, for example, we want to say something like, after initializing the balance to be some value over here, we want to make sure the resulting states should maintain the class invariance. And also, after withdrawing some amount from the balance balance of the account, we also want to make sure the resulting state is actually satisfying invariant. So invariant, you can think about, is checked at the end of each method after the implementation is executed. So now in this case, exceptions would not be the way to go. Instead, there's something called assertions. For those of you who might be more experienced with Java, you may have seen assertions already. But if you download the source code I provided to you, we do have the source code there. You can actually try it out yourself to see how they work. Okay, we can use assertions. So for example, for the CS major students, we're going to check after the execution of every method. So basically, after, we're going to say, I'm going to show you the code in just a moment. After the constructor, we're going to check to make sure the balance is larger than 0. Also, after the withdrawal, also we're going to check to see the balance is larger than 0. That's something you will see in version number 3. But one thing to note is actually one of the shortcomings for having assertions. Remember what I mentioned before. If you actually got, let me get there once I show you the source code. It has to do with about the public interface for assertions. Okay, and also for binary search tree, we can say assert, and then we say this, which is a binary search tree, get it in order sequence, in order traversal sequence, it should be sorted. I'm being a little bit informal here. Of course, you can think about how to express this in predicate logic. You may have to use a universal quantification to actually specify this. However, how would you do this in Java? Well, in Java may not be so straightforward. It's doable, but may not be so convenient. You may need either lambda calculus, or you might need actually a for loop or while loop to calculate the predicate result. However, in the design level, it would be very useful if we can specify such predicates in a more direct syntax, and IFO does support this for the design purpose. Okay, unlike exceptions, so now this point is very important. Let me emphasize that. Exceptions actually occurred in the API of your method to say this particular method throws, for example, division by 0 exception, like what we illustrated previously. However, whatever assertions you put at the end of your method will actually throw your method. Assertions are treated as private assertions, so they are never shown to any clients of your method. So clients do not necessarily know about this class invariant over here that you're checking. So that's one drawback. But there's other even larger drawback. We'll see. Okay, we're going to create version number 3, and then we'll see how the assertion goes. Okay, so now we got account v3, version 3, and then the only thing that's new is for the constructor over here. Okay, remember the negated precondition from the previous version, and now we're adding to say, so now we do the normal implementation over here to say if the error does not occur, we're going to assign. We're going to initialize the owner and also the balance. And now at the end of the method, you can think about it's almost like at the end of the constructor over here, we are asserting something. You will see some similar assertion at the end of the withdrawal as well. So at the end of each constructor call, we had to assert this balance should be larger than 0, and then we can give some messages. So let's say if the invariant, if the assertion evaluated to false, we're going to get some assertion error, and then with this message to say invariant should be, the balance should be positive. Okay, and we have to do such check, the end of the method check for every method, right? So now in the case of withdrawal, remember these are these two. Condition number 1, condition number 2. So these are the two negated preconditions from the previous version. So now this is the actual implementation if the inputs are valid. And now at the end of the method, we also check this assertion for the class invariants. Now you can see line number 8 and also line number 17. They are identical. Agree? Okay. That means we have, depending on how many methods, or how many constructors, how many accessors, how many mutators, if you have a very large class, the number of methods you have will be huge. You may have, let's say, 50 methods in your Java class, right? And then, in that case, how many times do we have to repeat such assertion at the end of each method? Depending on how many methods you have, you got 50 methods, repeat 50 times. If you got 99 methods, repeat it 99 times manually, right? every time you create a new method, you always have to copy and paste this particular assertion and put it at the end of the method. And now there's a design principle called single choice principle, which I'll elaborate later in the later lecture. Let me just mention quickly, just to give you some intuition. When we have so many repetition or duplicates of the same line of code, like assertion in this case, the bad thing is, what if later, let's say at some point, we decide we want to change the invariant condition. Rather than strictly larger than 0, let's say, we want to change it to larger than 100. Let's say the minimum balance for each account should be 100. So now, is there a single place that we can modify in order to change the invariance? Well, for example, in this case, the same invariance is repeated twice. Is there a single place we have to change, or two places? The answer is we have to change two places. We have to change larger than 100 over here once. And also we have to manually change larger than 100 twice. Depending on how many times the same assertion is repeated, you have to change this many times. It's been repeated 50 times, you got to change 50 times. It's been changed 99 times, you got to change it 99 times. So this actually violates a design principle called single choice principle, which we'll talk about later. But at least intuitively you can see having duplicates of the same code or assertion throughout your Java class is definitely not a good sign for your developments. Okay, try to absorb as many as possible. I think these are all good design principle that you're gonna hopefully you will eventually get soon. Okay, so let's see. How about the clients over here? And now let's say we got 100 over here, initial balance, and now after withdrawing 100 over here, so the resulting balance should be 0. So you can think about it's like one of the resulting balance over here. Let's say eventually after here, so we say balance is simply equal to 0, right? If that's a resulting balance, and then when we try to check the class invariant over here, we check it, it's going to be false, right? So now, so that basically balance will be equal to 0. So 0 larger than 0 is going to give you false. So now in this case, you get some assertion error, or conceptually class invariant violation. Okay, so now by encoding such class invariant checks at the end of each method, we are able to check to see every resulting state from your mutator call should result in some should result in some valid objects according to the class invariants. Okay. All right. So let's talk about and over here. Okay, that's the assertion error you will get. Okay. Maybe I should really show you very quickly. Okay. So that's the version number 3 over here. And then I'll just leave it clean so you can also look at that. Okay, again, so I don't mind, if you don't mind, let me just repeat very quickly. Okay, so now you can see this is repetition number 1, this is repetition number 2. You got repetitions, right? The same. Until now, there's a change on the requirements. Let's say, so now it should be balance larger than 100 as I said before. So now I said verbally described previously, you have to manually go here, and then change that to 100. Not enough, you have to also go here and then change it to 100. So this one here, so that means a change involved multiple places affected. You have to manually change multiple places. So this is a warning sign for your design. It violates the so-called single choice principle. Whenever there's any change in your design, there should be only one single place that get affected, not multiple ones. So single choice principle is actually a very fundamental one, which we will see many examples, either violation or satisfaction later on in the course. But it might be good to pick it up intuitively from day 1, from lecture 1. Okay, so now let's take a look to see what else we want to see. So now it does, by adding the class invariance as assertion right now, it resolved the issue from version number 2. So let's see how so. So now you can see over here, by creating this supplier object over here, Jim, with initial balance 100. So now after withdrawing 100, so now the resulting balance would just be 0. 100 decreased by 100. So now, when you can think about this one here is calling withdraw. So when we call the withdraw method here, basically we execute this part here. So this is something you should know already from the previous illustration. So now after this, we know that after such decrements of the amount, right? So basically we talk about we are trying to withdraw 100. We are trying to withdraw $100 from the account, and the current balance is actually 100. So after that, it's going to be this balance will become 0. So now, when you actually check for this particular assertion, 0 larger than 0 is going to give you false. So you have assertion error. So this is why when you actually execute a code in Eclipse, you will see assertion error. And then invariant should be positive balance. Okay, so hopefully you can see the execution. Again, I'm just executing the code on the paper. So you should really try that on Eclipse as well, just to convince yourself this is really how it works at the runtime. Okay, so now finally, before we end this part, we have to think about what else is really what else can be improved on this version number 3. So far, let's have a quick summary. From version number 2, we added negated preconditions as exceptions. And also for version number 3, the current version, we added assertions at the end of each method repeatedly as class invariant. And now, so that's what we have, right? So it's getting, again, quite complicated. Every method, imagine this. When you bank account is just a simple example. If the example gets more complicated later, you may have multiple methods. You may have a large number of methods in your class. And for every method, maybe the number of preconditions you have to check will be large. And also the number of class invariance conditions you have to check will be large. So now that means you're going to have a large number of branching conditions for exceptions, for preconditions, right? And also you're going to have a large number of assertions over here for class invariants. So you can see the supplier's code gets, again, convoluted. It would be very nice to have some syntax notation that will give you more direct notice about what's really expected from the supplier, rather than having assertion and exception. And also, even worse, assertions actually do not appear publicly on the interface for the methods. If you generate JavaDoc, the JavaDoc is not going to show the assertions. Okay, so now we want to identify one more limitation for this particular version over here. You can see, let's say for the withdrawal, we have, let me just go there and then illustrate to you. What's really limited for this particular version over here? Think about this condition over here and this condition over here. So these are the negated preconditions, I'll say approximately preconditions. And they are the obligations for clients. Okay, first of all, the preconditions. And then this part over here is actually the class invariants. And to really maintain the valid states for your business object is the supplier's responsibility, because supplier should make sure whenever the supplier creates the account object for you, they should be valid. They should be under no time that the account objects the supplier supplies to you should have negative balance. So that should be obligations for supplier. Okay, so now, So this, when I say is there any obligation on the supplier of withdrawal, yes, there's one, to make sure every time at the end of the implementation takes effects, the balance must be larger than 0. But now, is this really complete? So let me put it this way. Let's say if the withdrawal, if the supplier didn't implement the withdrawal correctly, and then rather than decrementing, let's say over here, rather than decrementing the amount from the current balance, we actually increase the amount from the current balance. So the implementation is wrong. Is the current class invariance good enough or complete enough to catch that error? Think about this issue here, and that will be the topic for the next video.